So here we are in the lab. I'm going to demo the 1480A USB analyzer and how to use it. So the basic setup is you need a host and a device that you need to test the communication between. So normally you would connect for instance, a USB key directly to the cable or directly into the host controller port of the host computer. But now, since we want to capture the data, we connect the USB analyzer in between instead, like this, straight into the front. And then the data will be captured by the 1480A, and we have a second analysis PC that will actually run the software that will display the captured data. So let's see how that works out. Okay, so I'm going to start with describing the front panel and the rear panel connectors on the 1480A USB analyzer, which is the current model USB protocol analyzer. The Kickstarter campaign is to fund a more advanced version of these existing products. So as you can see on the front panels, you have two connectors right here. One you connect to actually the device under test, and the other one to the host under test. So you connect this one right in between, the cable going between your computer and the device you're trying to determine the communication with. You have three LEDs on the front panel. One is the host power LED. This turns on whenever the rear connector is connected to the to your analysis computer and the device driver is installed properly. Then this will turn on. The link power is turned on whenever there's a 5-volt power to any of these connectors, and the link activity is whenever a packet is detected being communicated on the front panel connector. The rear connector, as it says, is supposed to be connected to the analysis computer. So let me hook this up so you can see what it looks like. So in this example, we want to connect and test the communication between a host computer and a USB flash key. It's a high-speed Cruiser Blade 32 gig flash key from SanDisk. And the analyzer analyzes both low speed, full speed, and high speed data. So it automatically detects the speed, so you don't have to configure that in advance. So simply what you do is you first hook up the USB analyzer to your analysis PC, which is the right PC I have over here. And then you simply plug this in the rear connector. And the host power LED turns on because it is now connected properly. If this LED is not on, then you have to install the device driver on the analysis PC to make it turn on. Okay, so what we do next then is to go to the 1480A application, which I have running here with an old trace in. So you simply click on the Start Capture button, and it says down here that down there in the corner, USB analyzer connected and capturing data. So then what you do is you simply connect the cable to the host, and then the host link power button here, or LED I should say, turns on. So off and on. I can do it a couple of times so you can see later in the trace, so you can actually see that going on and off. And then what you do is you simply connect the flash key, and you have communication. Immediately shows up in the window over here. And in this trace on the analysis PC, first of all, let me stop this so it doesn't collect too much data. So I just disconnect the flash key, disconnect the power, and then finally I can go here and stop the capture. Okay, so now the interesting thing, of course, is to see what can we capture on the bus under test. So you see here that the capture was started at time 0, and then you can see that the bus power was turned on and off 1, 2, 3 times, and that was because I plugged and unplugged this cable a couple of times. So you can see that in the trace. You also see that the device was connected all high-speed devices actually connect as full-speed devices. The device then goes through the device chirp sequence. As you see here, down here, it transmits a certain pattern of K's and J's on the bus to let the host controller know that it is a high-speed device. Then if the host controller is also a high-speed controller, then it transmits host chirp. And by doing that, both the device and the host knows that they're both high-speed devices, and therefore the transceivers of both the USB key and the host controller turns into high-speed mode. And that's exactly the same thing that the 1480A protocol analyzer does. And therefore you can track the connection speed. First connects as full speed here, and then connects as it turns into high speed mode, and then the communication continues. Now then, what kind of communication does a USB device do after it connects? The first thing it actually does is the host sets an address for the USB device. By default, a USB device connects as device number 0, and in this case there wasn't any other device on the bus, USB bus, so the host controller assigned address 1, and afterwards all the communication is done to device number 1, because that's the device number after it's been set that the device will respond to. And then the host controller retrieves a number of descriptors. A descriptor is something that the host controller, or I should rather say the host controller driver and the operating system uses to figure out things about the device. So for instance, here you can see that the device is a SanDisk Corporation device. The product ID and the product, let's see, the vendor and the product IDs, I should say, in combination determines which device driver to load for the device. Then you have configuration descriptor being requested from the device, and you can see here that the configuration descriptor is comprised of a number of different structures. So first you have a configuration structure, says whether it's bus powered, how much power it draws, and so on, and also the number of interfaces that the device supports. So here this device only has one interface, which actually uses 2 endpoints, and the interface class, interface subclass, interface protocol, and so forth actually probably just says that this is a mass storage device, because the device is a USB flash key. Further down you can see the details for each endpoint. You can see there's a bulk endpoint with 512 bytes packet size, and that is the maximum packet size for a bulk high-speed transfer. Further down in the trace you can see that there is communication. So the host here requests data from the device. It says device number 1, give me data from endpoint 1. An endpoint is simply a buffer in the inside this device. You have a little custom ASIC. Inside that little ASIC you have buffers, data buffers, that can be read and written by the host. And in this particular location the host says, give me the data in endpoint buffer number 1, and the device says, NAC, I don't have any data. And actually if you go through this trace here, you can see that there are a lot of these NACT transactions. So what we have up here in the filter menu, you can actually hide the NACT in transactions. And what we can do also, we can hide the start of frame packets, because they also clutter the display. So let's just do that, and then you can see the communication in more detail here. So you see here in the payload column all the data. So you have here an out transaction, and that is data sent from the host to the device, and here we have an in transaction, and so forth. So if you want to scroll down a little bit, you can see where the bulk data, the full size data, is being transferred. You can see here, for instance, there's an in transaction the host is reading from the device. It starts with an in packet, and then you have a data packet. Could be data 0, data 1, or data 2. Right now it's a data 1. Next one it becomes data 0. It alternates between those two. Data 1 again. For a given packet, you can go down here to the packet details view. You can see exactly which PID was used for that packet, the amount of data, and whether the CRC is valid or not. If you want to see the payload, you go down here to the payload view. You can see all the ASCII and hex data. These are all zeros here. You can go and find a little bit more interesting data, perhaps down here. Scroll down a little bit. This one is some kind of hex data in this area. Also for packets, the USB analyzer 1480A decodes all the packet information in these views, and it does that for packets, and also, if you go back to the beginning, it does it for the configuration descriptors. So anything that can be decoded, it decodes. Anything else, like host chirp, it prints here some information that's essentially lifted from the USB spec version 2, so you can more easily know what's going on. So let me go through the other views here. You have the details view. I talked about that. It decodes the packets. For instance, the data packet here, or a device request. Search results, you can search for something. I can show you that a little bit later. Markers, you can set in a given marker here. You can add a marker. You right click and you go add marker. We just write marker number 1, and you click OK on that, and then you see here that the marker is set to a data 0 packet at this timestamp here. So for instance, if there's something interesting going on around that time, you can even go and right click and you can set the timer reference. That means that all the timestamps are referenced to this particular location. Node Finder is a very useful view because it shows you all the known packets and bus events that occur in the trace. So for instance, if you want to see all the data 0 packets, data 1 packets, so on in the trace, you can just click on this and you go to next, and then the analyzer will instantaneously go in and find those packets for you. Token packets are the same, so all in transactions, you can walk the list of those, out packets and so on. Bus events, you have one device connection because we only connected one. The device was reset 5 times, etc. Same for handshake packets, transactions, device requests. You had one set address. We talked about that before, when the address of the device was assigned from the default 0 to 1 here. Let me move this a little bit to the right so we can see more. Here we have a get descriptor, and this is very useful if you want to debug your own firmware device to make sure that it returns the correct information in the descriptors. Otherwise, using a regular software-based so-called USB protocol analyzer, which is actually not a protocol analyzer at all. It's more a tool that shows you the data only. you will not see this information, anything related to the descriptor. And you will actually not see any of the stuff that shows up in the top window here, because this is all low-level USB protocol. So any software tool will not be able to show you any of the information you see in the screens here. And also you have one invalid packet. That often happens when you disconnect the device, because you get some garbage at the end there as you unplug the device. The analyzer also decodes on the go events, which is session request protocol, host negotiation protocol, and VBus changes. So that's the bus voltage on and off. That could be very useful if your device or hosts, or let's say that your device draws too much current, so the host cannot keep up the 5-volt level or the minimum level that's required. You can here see the actual levels for the VBus device voltage or bus voltage to be valid. It has to be more than 4.4 volts. It says right here. This is from the USB spec 2, and so on. So you can see if the voltage gets too low, it will show up here, and that could actually be cause for data communication. So that's something very, very useful if you're debugging intermittent communication issues. And here you have the capture started and capture stopped. So that was the node finder view, very, very useful. Payload view is something if you just click on a packet, transaction or packet, then the payload shows up. Let me see if I can go back to one of those larger transactions here. Scroll up a little bit. Here we go. This is only 31 bytes. Let's see if we can find a 512 byte with something more interesting than just zeros in it. No, all zeros. Okay. Anyway, let me click on that. So you see here that when you click on an in transaction or even the data packet within the transaction, the view here decodes the data and shows you it also in ASCII, which could be very useful. Another feature that's completely unique of the international test instruments 1480A protocol analyzer is that it actually shows you the lowest level data as it appears on the bus here. So all the packets in the trace, if you click for instance up here in the protocol view, which is the big view at the top, if you click on any transaction or any packet here, you can see that the message view actually automatically moves to this same location in the message view. So essentially what you're looking at here in the message view is the data that's being received from the ISP 1505 ABS PHY, which is used in the protocol analyzer in the 1480A. And this is the raw data that comes back. And it shows you RX active, for instance, here means that a packet is about to be received. VBus valid is a flag that tells you that the bus voltage is valid. Data 0 and data 1 directly shows you the D plus and D minus signal states on the line. So this is actually the lowest level differential state of the line. And this is something that's unique with the 1480A. No other USB analyzer has that feature. All other USB analyzers only show you the high level protocol view. And this one down here actually allows you to first of all confirm that the higher level protocol decoding and display is done correctly, because sometimes of course the software could make mistakes. So in here, if you click for instance on the next packet, you see that data 69 is the beginning of an in packet, and here you see that the PID of that packet is actually hex 69, so that's correct. So that's the purpose of the message view. Discover devices view will show you all the known and unknown devices that have been communicated with during the capture. So here you see that this is a crucible blade, which if you look again at the flash key here says cruiser blade, so that's correct. And here is all the information about that. So you can go to the device descriptor up here and get the information. And then let me close this here. Afterwards in the trace you get a configuration descriptor that shows you all the details about the device. Let's see if there's anything up here. You have capabilities to print the trace to a printer. This could be an extremely long operation because in the 1480A there's currently no way to only print a subset of the trace. So what you end up having to do is wait for this to print, and then you can print it to PDF, and then you can print a subset from the PDF in the PDF viewer. As I'll explain later in a different demo video, the existing 2500 PCI Express protocol analyzer, which I actually have over here. This is the PCI Express version of a protocol analyzer. This has a much more advanced software, and that's the purpose of this Kickstarter campaign, is to integrate all the advanced features of this protocol analyzer into the existing 1480A, and therefore arrive at a 1480B. And in the 1480B then you would have a much more, I'm going to stop the printing here in the view because it takes too long. You will have a actually much more advanced printing interface, but the main idea here is that you can print the data in the trace, and as you can see here it's not formatted correctly because the window was too wide, and that's another feature that's available in the 2500A software that will be incorporated in the 1480B, the new USB protocol analyzer. So there will be vastly improved printing support. Also there is a search feature here that allows you to search the data packets for string data, either in Unicode or ASCII or hex data. So what we can do here, since we know that this is a cruiser blade device, we can actually figure out, and also we want it case insensitive because we didn't put in caps here, although it was actually reported as capitalized wording down here. So if we kick off the search, then the search results view here shows that it found 2 matches, so we can go and see where the analyzer is actually getting that cruiser blade information from that it shows here in this window. And you can see then, if you go back to payload view here, you can see that this was part of the get descriptor, string descriptor. So if you go to the details view, you can see that the string retrieved was cruiser blade, and this is the raw ASCII data. And if you even want to go all the way to message view down here, you can see the data show up here. So the data is actually coming from here, so you should be able to go to this packet, go to the payload view, and there you go, cruiser blade. And then you have the filter protocol items view. We briefly visited that dialog before. Here you can hide a lot of things that clutter the display. Top level out transaction, that's if you're only interested in the in transaction, you're not interested in the out, so everything related to that, the out transaction, will be removed from the protocol view. You can do the same for the in transactions. You can also hide ping and split transactions, any invalid packets, you can hide that too. Start of frame packets, you can see what it looks like if we uncheck that one and it will reparse, and then you see here that startup frame packets will show up in the trace. And you can see also that the frame number is being incremented 0, 1, 2, 3, 4, 5, 6, 7, and then it turns to 1231, 0, 1, 2, 3, 4, 6, 7, 32, and so on. Goes up. So that works the way it should. So if you're debugging your embedded device and it doesn't properly work, then it could be because of maybe you're not handling the frame numbers correctly. So that's another thing that only a hardware-based USB protocol analyzer can help you debug. To go back to the filter dialog here, you can hide all the device requests. So for instance, if you do that, let's hide the startup frame packets too. If you go back, so now you see that so it still finds this view, but it actually doesn't display it in the main protocol view, right? So now you see in the beginning you don't have any get device descriptor and get configuration descriptor in the trace, because you we check this here. So if you uncheck that, it will show up in the beginning again, all the device requests from here and down. And you have the same thing here for bus events. You can hide and display these things. Another handy feature is if you have multiple devices on the host controller connected to the same host controller, you might get some ghost traces or ghost data in the trace that doesn't belong to your device, and that could be because the host controller is actually a broadcast device. So any data that's being sent down to one cable segment from the host controller actually shows up on all the cables going to other devices. But of course, a device only responds to its own address. So here you see set address 1 for our device, and therefore our device from this point on only responds to device address 1. So you can see the way this works here. In the setup transaction, you have a setup packet, and in the setup packet you have a device number of 1 in here, and therefore the device, our device, the SanDisk Cruiser Blade, only responds to that device number 1. So in case you have traffic with to multiple devices in the trace, you can just go here and you can, for instance, say I want to block traffic on device 2 to 3 plus 5. Let's see, 2 to 3 and 5. You can also block some particular endpoints if you have endpoint, I don't know, 1 to 2, for instance, and then you okay that. Right now we don't have any devices with device ID 2 and 3 and 5, so this doesn't make any difference in this capture, but it's good to know that you can hide traffic to other devices if you need to. I should say something about timestamps too. If you go here and you open this view, you can see that if you want to measure the time between two timestamps, first of all, let me get rid of the time reference. If you want to measure the time from this packet to this packet between these two, it's hard to do. So what you could do is you right click and you can either set the time reference to the first packet, and then you see that it's 350 nanoseconds between those two packets. Or what you can do is you can clear the time reference. You can simply set to relative timestamps, and then you see that it's 352. So the timestamp shown is the time from the previous packet to the packet indicated. So let's set it back to absolute, and and then markers, I showed you that before, so there's nothing related to that. more to describe, I think. Then, of course, the capture is very simple. You just start it, like I showed before. You plug in your device. I'm gonna do it again here. And the data shows up, and we stop the capture. And here we have our cruiser blade device again. So this is the 1480A USB protocol analyzer, version 4.10. Okay, so this is the PC board inside the 1480A protocol analyzer. So if you recall, before you had the front panel connectors right here, the LEDs that uses the light gate to connect to the front panel. In here you can see this little thing here is the actual PHY used to snoop on the data. So the connectors is a pass-through, so the host is connected to one of them here. The traces here go straight out to the other connector. So the PHY simply snoops on the existing data path between the host and the actual device that you're analyzing traffic. You can see here it connects to the Cyclone 2. It's upside down because that was the best layout of it. The Cyclone 2 then takes the data that comes out of the PHY here, and it puts it into a Micron SDRAM. This is a 32 megabyte SDRAM. The data then goes from the SDRAM into this chip here, which is a USB 2 microprocessor from Cypress. This is an FX2 LP, which then sends the data through this cable here to the analysis PC. So as you can see, it's quite simple hardware design of a USB protocol analyzer, but of course the complexity is all about what's inside the FPGA, and it's actually quite complicated to accomplish everything that goes on here. The 1480B USB protocol analyzer, which is the next version of this one, will have essentially 4 of these SDRAMs underneath here, 64 megabytes each, for a total of 256 megabytes capture buffer. Apart from that, the design is expected to be fairly similar to this one. Possibly, if there's an advantage, I could upgrade the FPGA to something a little bit newer and larger, but for backwards compatibility and cost, for cost reasons, I might just stick with the same. So that's how the current design looks.